Welcome to a lesson with Dr. Powell. Let's take a look at an example of L'Hopital's rule when we don't have a fraction at first. So what if we had something like cosine of x raised to the cotangent of x? Okay, so in looking at this, we don't see a fraction. However, if we apply a natural logs, or any logarithm for that matter, are very nice at changing things into multiplication or addition or subtraction when they were other things before. For instance, if we have exponentiation, that can turn into multiplication. So that cotangent of x times natural log of cosine x is what we have. Just a reminder, this is the exponent. So natural log of cosine x is the exponent that you'd have to raise e to get to cosine. Well, that exponent times this exponent is the exponent that e would have to be raised to get to this. So that's just a statement of that. So we get this, and now is multiplication a fraction? Well, it sure leads to one, because multiplication is the same thing as division by the reciprocal. So whenever you see multiplication, you really do have a fraction. As follows, we just take the reciprocal of this, and that's what we're dividing by. So this is what we have. So notice that we started with cosine x, cotangent x, and see what we did. We modified it into a fraction. The way we did that is we had to put this inside of a natural log. So really what we're doing is if we were doing a limit, we would be computing the limit of the natural log of something. But really what we want to compute is something like this. E to the natural log of this, so that these guys undo each other and you're just left with that. But this is essentially what we're looking at. Let's suppose that we're taking a limit as x approaches 0. Now notice that this limit can pop inside of the e here because e is a continuous function. So we really can look at e to the limit as x approaches 0 of natural log of cosine x to the cotangent x. So this tells us that whatever we get right now, right here, we better put it as an exponent for e to find the ultimate limit that we were after originally, which was the limit of cosine x raised to cotangent x as x approaches 0. That's the limit that we're ultimately after. And we're going to get it by finding this limit and then putting it as an exponent of e. Okay, so let's get started on this. First, can we use L'Hopital's rule? It's a fraction. Well, we have to check, because many fractions we can't use this on. We have to make sure that the top is heading toward like 0 and the bottom's heading towards 0, or the top's going to infinity and the bottom's going to infinity. So plus or minus would be fine. So let's see what we can do with that. As x approaches 0 on the top, we get natural log of 1, which is 0. So that's going to 0. The bottom, you plug in 0. Hey, that's going to 0 as well. The tangent is equal to 0 at 0. So we can use L'Hopital's rule. Awesome. Let's see what we get. Let's see if we can do this. So let's go ahead and remember what the limit that we're taking, and let's go for this. So we have natural log of cosine x all divided by tangent x, and we're going to take and we're taking the limit of this as x approaches 0. Okay, so by L'Hopital's rule, this is equal to, we can take a derivative of the top, 1 over what's inside, but then we have to, by chain rule, have to multiply by negative sine x. And then this is all over the derivative of tangent x, which is secant squared x. Awesome. So we just turned this limit into a limit that doesn't have any natural logs. It just has trig functions. Why don't we do a little bit of playing around with trig functions for a minute and see if we can do some kind of simplification at this point, just with trig functions to make our fraction look nice, and then maybe we'll see where we can go from there. So let's see. So secant squared is 1 over cosine. Just keep that in mind. 1 over cosine squared. So 1 over cosine squared in the denominator would be like popping a cosine squared on the top. That's not that like this. Or you could think of multiplying top and bottom by cosine squared. And then here, that cancels with that. So you just have 1 of the denominator. So we're left with this. Now, cosine squared and cosine x, notice that you have that guy and that guy can cancel, 1 power there and 1 power there. So we're just left with the limit as x approaches 0 of negative sine x multiplied by cosine x. Now this is great because we can just plug in now, because we don't even have any denominators, so we're not going to have any place that's undefined. But you can just, and sine and cosine are defined everywhere. So if we plug in 0, notice we just end up getting 0. That's awesome. But let's remember that's not the ultimate limit. That's just the limit of this. Remember what we had to do with it? We had to say e raised to it. So the ultimate limit that we're after, which is the limit as x approaches 0 of the cosine of x raised to the cotangent of x, is actually equal to e to the 0, which is equal to 1. Kind of surprising. So the limit of this is actually equal to 1. Now let's just think about what this looks like originally. Here. So if we have, as x approaches 0, the cosine of x raised to the cotangent x. So as x approaches 0, this guy is going toward 1, and the cotangent is actually heading off to positive infinity. If you think about it, it's cosine over sine, and your sine is going to 0 through positive numbers. At least if you're on the, we really should do this from one side. The limit as x approaches 0 from the right side, and that would make it work. Okay, yeah, so really this should be a one-sided limit to really make the cotangent go off to positive infinity here, I guess, in this particular case. Okay, so just for looking at this, so we have 1, and we're raised, so it's kind of like saying 1 as like something that's heading toward 1, and then you're raising it to something that's like going toward positive infinity right here. And that's kind of what we're looking at. 1 raised to some big power here. Now, if you take a look at this for a minute, just think about this idea, natural log of 1 to infinity. What does this look like? This kind of looks like infinity times, this is just loose. This isn't real math. This is just kind of thinking about things intuitively, which looks a little bit like natural log of 1 over 1 to infinity. And this looks a little bit like 0, and this looks a little bit like 0. So in some sense, if you ever have a form that looks something like 1 to the infinity, we might have to use something of this type right here. Now you might say, okay, well, in this case, we got 1 from this, and I should expect 1 to anything is just going to be 1. So I don't really believe this quite, Dr. Powell, that we need all this jazz to get what this is. I think this is well defined. Well, let's look at another example where it's not. Thanks for watching.